So yeah, traditional emotion recognition systems process the whole utterance at once, ignoring the emotional variability that can occur during the speech. So this prompted us to investigate segment-based processing solutions. And additionally, we incorporate a triplet loss into the learning framework to increase the interclass separability. So to this end, we demonstrate that our multitask learning framework, which combines together the segment-based processing and triplet loss, improves the spoken emotion recognition result on 3 datasets, 2 in English and 1 in Finnish. So just some small description about the datasets used. The first one is IEMOCAP, which contains about 7 hours of English speech with 10 speakers and emotional labels, neutral, sadness, happiness, and anger. Then the second database is called RAVDESS, which has 3 hours of English speech with 24 speakers. And the emotional labels are neutral, calm, happy, sad, anger, fearful, disgust, and surprised. And then the third dataset is a Finnish dataset, Finnish emotional speech corpus, which has around 5 hours of Finnish speech and 9 speakers with emotional labels, neutral, sadness, joy, affection, and anger. And then during evaluation for the IEMOCAP and Finnish emotional speech corpus, we used k-fold cross-validation. Okay, now I start off with the method. In this figure, we can see our proposed method. So first off, we have the training sample as triplet. So we have 3 audio samples, 3 raw audio sample where A represents the anchor. Then P represents the positive sample, which is from the same class as the anchor. So they both have the same emotional label. And then N represents the negative sample, which is from a different class. Then we use a wave-to-vec2 model to extract features from each of these raw audios. Then the next step is to segment those wave-to-vec features into segments with overlapping window. So that's how we get these 3 segments. And then we extract the utterance probability first on the left side. So we actually attach an output layer with the softmax function to get the utterance probability from the green part, so from the whole utterance, but also from each of the segments. So from this part, we also get the segment probabilities. Then on the right side, we have the actual triplet loss, where we either do the triplet loss on the segments or on the whole utterance, as on the right with W. So we either do it on the segments or on the actual whole wave-to-vec features, but we don't do them together, but we either try one or the other. Then the next step is to compute the loss functions. So first on the left side, we compute the utterance level negative log likelihood, and then the segment level negative log likelihood, where we basically sum all the segment losses, and then that's how we get the classification loss. And then we combine that classification loss together with one of these triplet losses, whichever we use. And that's how we get the final loss. All right, now we go to the experimental setup. So we use 2 evaluation metrics. First is unweighted average recall, and the second one is unweighted accuracy. And then in the multitask learning, we use the following formula for combining the negative log likelihood and the triplet loss. So basically, we have an alpha weighting factor which weights both loss functions. And then on the right side in the first plot, we can see how the alpha changes on the RAVDESS dataset. As we change the alpha, how the unweighted average recall changes. So based on that, we found that the alpha value of 0.7 works the best with the model only using triplet loss. But for the multitask model, so the one that uses the segments in the triplet loss, 0.1 of alpha is the best. And then for the multitask model using the whole utterances in the triplet loss, 0.2 is the best. And then for the other databases, we could not select the appropriate alpha factor because we are using k-fold cross-validation. And we found that for different folds, like different alpha is the best. So it was difficult to pick it. So that's why we did not use. We also tried to make alpha a learnable parameter during training, but that did not also improve the results. Then we also experimented with different segment sizes. So in the second plot, we can see how the unweighted average recall changes with different segments. And basically here I want to point out that segment size of 100 is roughly 200 milliseconds in audio. So we found out that for IEMOCAP, a segment size of 140 is the best. For RAVDESS, smaller segment size work better with 80. And for the Finnish dataset, again, 120 is the best. Then we're also using a sliding window, and the stride size is always half of the segment size. All right, now we come to the results. So first we can see the wave-to-vec2 baseline. And for this baseline, we basically use the wave-to-vec2 model and added a classification layer. And then we can see that if we use the segments, so if we just use segment-based processing, we already get better results in all the 3 datasets compared to the baseline. But then if we add the triplet loss, the benefits are even greater. So there is even bigger improvement compared to the baseline. And then naturally, by combining the multitask learning framework of segment-based processing and triplet loss gives the best results. And then for the IEMOCAP, it's best if we use the segments in the triplet loss, while for the other 2 datasets, it's best if we use the whole utterances in the triplet loss. Then we also compared our models to some of the literature. So for example, the first model is wave-to-vec2 PTAPT, which used to be state-of-the-art. And this model basically modifies the pre-training objective of the wave-to-vec2. So they pre-train it in a different way so that it can take into account the emotions. And our model performs slightly worse, but is still comparable. And also on the RAVDESS dataset, we found also some benchmark. But here they are using all of the wave-to-vec2 layers together, using layer averaging, while in our case, we are just using one wave-to-vec2 layer, either the last one or the second to last one. So that's why our result is a bit worse. But then their model is not that robust because on the IEMOCAP, they get 67 unweighted average recall, while we get a bit better. Then we also tested how the segment-based processing affects the long and short segments. So for example, for the IEMOCAP, we got all the utterances in the test set that are shorter than 10 seconds. And in that case, the segment-based processing improves the results. But then contrary to that, for the longer segments, which are like bigger than 10 seconds, the results are a bit worse using segment-based processing compared to the baseline. But then on the Finnish dataset, we observed improvements in both short and long segments when using segment-based processing. Then on the other table, like table 2, we treated the best models predictions as true labels and try to see how much those predictions agree with the other models. So as expected for the IEMOCAP and RAVDESS datasets, if the best model was this one, let's say for the IEMOCAP, the wave-to-vec2 plus triplets on the segments, then as expected, the biggest agreement is with the other multitask model, which uses the whole utterances. It's similar with the RAVDESS, but then the interesting thing is on the Finnish dataset, where the biggest improvement was with the model only using the triplet loss, which suggests that here, in this case, the model learns different stuff, whether we use like the segments or the whole words in the triplet loss, the model will learn to make different mistakes. So they learn different stuff. And to wrap things up, in this work, we presented a multitask model utilizing segment-based processing and triplet loss for spoken emotion recognition. We showed that segment-based processing improves the model's robustness in short utterances, but for the long ones, there's a small performance drop on the IEMOCAP, but improvements on the Finnish emotional speech corpus. And we found that using segments or whole utterances in the triplet loss can lead to the models learning different things, making their predictions differ. Yeah, that's all. Thank you.